Hello, and welcome to Space for Sleep. Consider a star much more massive than our Sun. For millions of years, it converts hydrogen into helium. Later, helium burning builds carbon and oxygen, and a succession of hotter, shorter burning stages produces neon, oxygen, silicon group nuclei, and finally, an iron-rich core. Throughout its life, perhaps only a few million to a few tens of millions of years, pressure created by nuclear burning resists the inward pull of gravity. Then the iron-rich core can no longer support itself. Iron marks the end of energy-producing fusion for an ordinary massive star. Combining iron group nuclei into heavier elements requires energy rather than releasing it. As the iron-rich core grows, electron captures and the breakup of nuclei begin to remove pressure and energy from the core. The balance that has supported the star fails. Gravity remains, and the collapse accelerates. The iron core, with a mass comparable to the Sun but a radius of only a few thousand kilometers, collapses in a fraction of a second. The inner core falls inward at a substantial fraction of the speed of light. Temperatures climb toward 100 billion Kelvin, and the central density rises through 10 to the 17th kilograms per cubic meter, approaching the density inside atomic nuclei. At those densities, electrons are captured by protons, producing neutrons and neutrinos. The inner core stiffens when matter reaches around nuclear density, and its sudden deceleration launches a shock into the material that is still falling inward. The shock does not simply raise to the surface. It loses energy by breaking heavy nuclei apart and by producing neutrinos, and it often stalls. In the standard picture of a core collapse supernova, an intense flow of neutrinos from the newborn compact core, aided by turbulent motion and convection behind the shock, transfers enough energy to revive it. The restored shock then drives outward through the star and helps produce the explosion. What remains of the core, if the star's mass allows it, is a neutron star. A neutron star is composed mainly of neutrons, together with smaller populations of protons, electrons, and perhaps more exotic particles in its deepest layers. A typical neutron star contains about 1.4 times the mass of the Sun inside a sphere roughly 24 kilometers across, although both mass and radius vary. Its average density is comparable to the density of an atomic nucleus. At that average density, a teaspoon-sized volume would contain roughly 1 billion tons of matter, with the exact number depending on where inside the star the sample was imagined to come from. These numbers do not correspond to anything in ordinary experience. They exceed, by orders of magnitude, the densities available in any terrestrial laboratory. The physics operating inside a neutron star, the quantum mechanical, nuclear, and possibly exotic particle physics of matter compressed to densities many times that of an atomic nucleus, is at the frontier of what current theory can describe and is almost certainly beyond what any Earth-based experiment can currently probe. Neutron stars are physics experiments run by nature at conditions we cannot replicate, and observing them is one of the primary ways we have access to the physics of extreme density matter. The route to that remnant begins long before the final second. A massive star spends most of its life in a state of balance called hydrostatic equilibrium. Gravity pulls every layer inward, while pressure created by hot gas and nuclear reactions pushes outward. The balance is never perfectly still. The core slowly changes its composition, the temperature rises, and new reactions become possible. Hydrogen burning may last millions of years. Helium burning is much shorter. Carbon burning may persist for centuries. Neon burning can last about a year. Oxygen burning may continue for months, and silicon burning can consume its available fuel in only days. The sequence becomes faster because the later reactions produce less useful energy, and because neutrinos carry increasing amounts of energy directly out of the core. Near the end, the star resembles an onion in cross-section. Different shells are burning different fuels at the same time. Hydrogen may still burn in an outer shell. Deeper inside, helium, carbon, neon, oxygen, and silicon burn in progressively hotter layers. At the center, iron group nuclei accumulate. The star may still look almost unchanged from the outside, while the internal clock is racing toward collapse. The word iron is useful, but the final core is not a perfectly pure ball of ordinary iron. It contains a mixture of tightly bound iron group nuclei under enormous pressure, together with a highly degenerate sea of electrons. Degeneracy pressure is a quantum effect. Electrons cannot all occupy the same quantum states, so compressing them forces them into states with greater momentum. This pressure can support matter even when ordinary thermal pressure is no longer enough. It is the same broad principle that supports a white dwarf, but the iron core of a massive star is growing and heating while nuclear and weak interaction processes steadily undermine that support. Two processes become especially important. High-energy photons begin to break heavy nuclei into lighter fragments, consuming energy that had helped maintain pressure. At the same time, electrons are captured by protons inside nuclei, producing neutrons and neutrinos. Electron capture reduces the number of electrons available to provide degeneracy pressure. The core becomes less able to resist gravity, and once instability begins, collapse feeds on itself. The inner and outer parts of the core do not fall in exactly the same way. The inner core collapses approximately as a coherent region, while material farther out falls inward more rapidly. When the center reaches nuclear density, the equation of state stiffens. The inner core rebounds slightly, and a shock forms near the boundary between the inner and outer collapsing regions. Early descriptions sometimes made this bounce sound as though it alone blasted the star apart. Detailed calculations showed that the situation is more difficult. The shock spins energy dissociating iron group nuclei into individual nucleons. It also loses energy through neutrino emission. Within a short distance, it stalls. The stalled shock problem was one of the central puzzles of 20th century supernova theory. The modern picture is that neutrinos, turbulence, rotation, magnetic fields, and asymmetries can all contribute. Neutrinos streaming outward from the proto-neutron star are weakly interacting, but there are so many of them that even a small fraction of their energy can matter. Behind the stalled shock, some neutrinos are absorbed by matter. Convection and turbulent overturn keep material in the heating region longer, allowing more energy to accumulate. In many simulations, this is enough to revive the shock and send it outward. The explosion is therefore not a perfectly spherical detonation. It is a rapidly changing three-dimensional process. Plumes rise. Downflows continue to feed the compact core. The shock expands faster in some directions than others. These asymmetries help explain why many neutron stars receive powerful birth kicks. A newly formed neutron star may leave the explosion moving at hundreds of kilometers per second. Some travel faster than 1,000 kilometers per second. Over millions of years, such a star can cross large parts of the galaxy, escaping the cluster or binary system in which it was born. The same asymmetry can affect the star's rotation. The collapsing core already has some angular momentum, and contraction greatly increases the rotation rate, just as a skater spins faster by pulling in their arms. Yet most newly observed young neutron stars are not rotating near the theoretical breakup limit. Angular momentum must be redistributed or lost before, during, and after collapse. Magnetic torques inside the progenitor, mass loss in stellar winds, binary interaction, and the dynamics of the explosion all influence the final spin. Not every core collapse leaves a stable neutron star. If the remaining core is too massive, gravity wins again. In some cases, a proto-neutron star forms briefly, radiates neutrinos, and then collapses into a black hole. In others, material that was initially thrown outward fails to escape and falls back. This fallback can add enough mass to push the remnant over its stability limit. The dividing line depends on the structure of the progenitor, its rotation, its composition, the energy of the explosion, and the still uncertain maximum mass that dense matter can support. The mass of the original star is therefore only a rough guide. Stars born with perhaps 8 to 20 or more times the Sun's mass can produce neutron stars, but the exact outcome is not determined by one simple number. A star can lose much of its envelope through winds or through interaction with a companion. Two stars with similar birth masses can develop very different cores. A somewhat heavier star may explode successfully and leave a neutron star, while another may collapse more directly into a black hole. Binary systems make the story even richer. A companion can strip away the hydrogen envelope before collapse, producing a compact helium star. Mass transfer can spin the progenitor up or slow it down. When the supernova occurs, the sudden loss of mass and the neutron star's natal kick can break the binary apart. One star may be hurled away as a runaway star while the neutron star departs in another direction. If the system remains bound, it can later become an X-ray binary, a recycled pulsar system, or eventually a pair of compact objects destined to merge. The newborn neutron star is initially hidden. The expanding supernova ejecta are opaque, turbulent, and bright. Deep inside, the proto-neutron star is still changing. It is larger than the cold neutron star it will become, perhaps tens of kilometers in radius, and it is filled with trapped neutrinos. Over roughly 10 seconds, most of those neutrinos diffuse outward. As energy leaves, the star contracts, the composition adjusts, and the familiar layered structure begins to emerge. A nearby core collapse supernova would announce this process first through neutrinos. In 1987, detectors on Earth recorded a small number of neutrinos from supernova 1987A in the Large Magellanic Cloud. Only a few dozen were detected, yet they arrived hours before the visible brightening and broadly matched the expectation that a collapsing stellar core releases an immense neutrino burst. The compact remnant at the center of that supernova has remained difficult to identify directly, but the neutrino signal gave humanity its first direct glimpse into the birth process of a neutron star or black hole. A future supernova in the Milky Way would be observed in extraordinary detail. Modern neutrino detectors could record thousands or even tens of thousands of events. Gravitational wave observatories might detect the changing quadrupole motion of the collapsing core. Telescopes across the electromagnetic spectrum would follow the explosion, while the emerging neutron star could reveal its spin, magnetic field, and kick. For a few seconds, several different messengers would carry information from regions that visible light cannot reach. That is one reason neutron star birth remains such an active field. The broad outline is understood, but the exact path from a stellar core to a successful explosion is sensitive to physics across an enormous range of scales. Nuclear reactions inside nuclei influence the behavior of a star thousands of kilometers across. Neutrinos with almost no mass help determine whether an envelope containing several solar masses is ejected. Turbulence on scales of kilometers influences the velocity of an object that may travel through the galaxy for billions of years. Once the remnant has settled, its gravity changes the meaning of ordinary words such as surface, height, and escape. On Earth, a thrown object can rise and fall through a gravitational field that changes only slightly over everyday distances. Near a neutron star, moving even a small distance can involve an enormous change in gravitational energy. For a typical neutron star, the escape speed from the surface is a substantial fraction of the speed of light. often around 1/2 to 2/3 of light speed, depending on the mass and radius. A particle falling from far away can strike the surface with tremendous kinetic energy. In an accreting system, each gram of infalling gas can release far more energy than a gram of matter undergoing ordinary chemical burning, and much more than a gram undergoing nuclear fusion in a normal star. This efficiency is one reason neutron-star binaries can shine so brightly in X-rays. Gravity also affects time. A clock near the surface runs more slowly relative to a clock far from the star. Light climbing away loses energy and is gravitationally redshifted. An X-ray photon emitted from the surface arrives at a distant telescope with a lower energy than it had when it began its journey. Any attempt to infer surface temperature, atomic composition, or radius from an observed spectrum must account for this redshift. The bending of light is equally dramatic. On an ordinary spherical body, an observer can see roughly one hemisphere at once. Around a neutron star, curved spacetime bends rays from parts of the far side into view. A hotspot rotating behind the edge may remain partially visible. This strong gravitational lensing smooths the pulse pattern from rotating hotspots. NICER's measurements depend on modeling that effect with great precision. The shape of an X-ray pulse is therefore not merely a pattern of brightness. It is a map of space-time curvature near the star. The same compactness produces intense tidal forces, but their character depends on distance. A person approaching a neutron star would not encounter a solid surface in any survivable sense. Long before contact, radiation, magnetic fields, and tidal gradients could be destructive. Near the surface, the difference in gravity between 2 points separated by the length of a human body could be enormous. Matter would be accelerated, heated, ionized, and incorporated into plasma. Popular comparisons sometimes invite us to imagine standing on the surface. It is more accurate to say that there is no normal place to stand. The atmosphere may be only millimeters or centimeters deep. Beneath it is a solid crust, but the surface temperature of a young neutron star can be hundreds of thousands or millions of Kelvin. The magnetic field may channel particles and radiation into polar regions. The gravitational acceleration is so great that material settles almost immediately into the lowest available configuration. The word solid also needs care. The crust is a solid in the sense that nuclei occupy an ordered lattice and can resist shear. It may be the strongest known material in the universe. Simulations suggest that neutron star crust can withstand strains far beyond those tolerated by steel. Yet it exists above a core that is expected to behave as a mixture of quantum fluids. A neutron star can therefore be thought of as a thin, extraordinarily strong shell surrounding a vast liquid interior, although the boundary between crust and core is complicated and may contain nuclear pasta. Rotation slightly distorts this picture. A slowly rotating neutron star is nearly spherical. A millisecond pulsar becomes wider at the equator and flatter at the poles. At the fastest observed spin rates, the equatorial surface moves at a significant fraction of the speed of light. Relativistic Doppler boosting makes an approaching hot spot appear brighter and harder in energy than a receding one. Time delays across the star also matter. Photons emitted from different points do not all take the same path or arrive at the same time. There is a maximum rotation rate beyond which material at the equator would no longer remain bound. The precise breakup frequency depends on the equation of state and the star's mass. The fastest known pulsars rotate below most plausible breakup limits, but not by an enormous margin. Their continued existence rules out combinations of mass and radius that would make them unstable at the observed frequency. Rotation stores a remarkable amount of energy. A young neutron star spinning dozens or hundreds of times per second can contain more rotational energy than the sun will radiate over millions of years. Magnetic fields and particle winds gradually carry that energy away. The rotation slows, and the lost rotational power can illuminate a surrounding pulsar wind nebula. The Crab Nebula is the classic example, but it is not the only one. Around many young pulsars, relativistic particles stream outward until they collide with slower-moving supernova ejecta or the interstellar medium. At the termination shock, particles are accelerated and radiate across radio, optical, X-ray, and gamma-ray wavelengths. The shape of the nebula can reveal the geometry of the pulsar's spin axis and wind. Rings, jets, wisps, and moving knots allow astronomers to watch the conversion of rotational energy into radiation almost in real time. A neutron star's compactness is often expressed through the ratio of its mass to its radius. This ratio controls gravitational redshift, light bending, surface gravity, and many features of its oscillations. Two stars with the same mass but different radii would produce measurably different pulse profiles and tidal responses. That is why the effort to measure radii to an accuracy of about a kilometer is so important. A kilometer sounds large in ordinary life, but for an object only about 12 kilometers in radius, it separates very different possibilities for the matter inside. The limit between a neutron star and a black hole is also described by compactness. If enough mass is added and no pressure can support it, the star collapses within an event horizon. There is no stable surface just above the black hole limit for ordinary matter. The transition is not a gradual darkening. It is a loss of all possible equilibrium configurations. For a distant observer, the final moments would be dominated by rapidly changing gravitational and electromagnetic signals. For matter falling with the surface, collapse would continue through the horizon in finite proper time. What happens to the dense nuclear phases during that transition is hidden from the outside once the horizon forms. Neutron stars therefore occupy a narrow and extraordinary region of possibility. They are compact enough for relativity to shape every observation, but not compact enough to hide behind an event horizon. They possess a material surface, a crust, magnetic poles, and often an observable temperature. They allow matter to speak from a gravitational field almost as strong as nature can produce without forming a black hole. The idea that neutron stars might exist was proposed only 2 years after the neutron itself was discovered. James Chadwick identified the neutron in 1932. In 1934, Walter Baade and Fritz Zwicky, the same Zwicky who had argued for unseen mass in the Coma cluster, suggested that certain violent stellar explosions might produce a compact object composed of neutrons. Their paper was remarkable for its intuition. They connected the observed phenomenon of supernovae, which they were the first to distinguish as a separate, more energetic category from ordinary novae, to the possibility of a collapsed stellar remnant of extraordinary density. The theoretical framework for neutron stars was developed in the late 1930s by J. Robert Oppenheimer and George Volkoff, who applied the newly developed framework of quantum mechanics and general relativity to the structure of a hypothetical neutron-rich compact object and derived the equation of state, the relationship between pressure and density, for neutron matter. Their calculation produced a maximum mass for a neutron star, approximately 0.7 solar masses in their calculation, which was revised upward by subsequent work that incorporated a more complete treatment of nuclear forces. The non-rotating maximum mass, commonly called the Tolman-Oppenheimer-Volkoff limit, is probably only somewhat above 2 solar masses and may lie around 2.5 solar masses, but the precise value depends on the still uncertain physics of the deepest core. For 3 decades, neutron stars remained theoretical objects, products of plausible physics, but without observational confirmation. They are extraordinarily small, and much of their detectable radiation emerges outside visible light. Before radio and X-ray astronomy matured, astronomers had no practical way to identify one securely. The theoretical predictions sat in the literature, occasionally cited but largely unconfirmed. Confirmation came from an unexpected direction, in one of the more dramatic stories in the history of astronomy. In 1967, Jocelyn Bell was a 24-year-old PhD student at Cambridge University, working on a new radio telescope array she had helped build, a forest of poles and wires spread across 4 acres of English countryside, designed to study the flickering of distant radio sources as radio waves passed through the ionized gas of the solar wind. Bell was responsible for analyzing the paper chart recorder output of the telescope, a task that produced several kilometers of paper per week, all of which she examined by eye. During 1967, after first noticing an unusual patch of signal in the chart records and patiently tracing its return, she and the Cambridge team resolved a series of pulses arriving at intervals of about 1.337 seconds, with extraordinary regularity, far more precise than any known natural phenomenon then recognized. Bell and her supervisor, Anthony Hewish, initially considered the possibility of a signal of artificial origin, possibly a distant, unknown civilization. The signal was given the semi-joking designation LGM1 for Little Green Men. But the signal did not show the slight Doppler shift expected if it came from a planet orbiting a star, and within weeks additional pulsating sources were found in other parts of the sky, each with its own period, making a natural astronomical explanation far more convincing. The theoretical explanation came quickly from Thomas Gold, who proposed that the pulsing signals were produced by rapidly rotating neutron stars, compact objects spinning many times per second, with a beam of radio emission sweeping across space with each rotation like a lighthouse beam. Each time the beam crossed Earth's line of sight, we received a pulse. The precise period of the pulsation was the rotation period of the neutron star. The extraordinary regularity was a consequence of the extraordinary stability of a massive spinning object. A neutron star, once set rotating, loses angular momentum very slowly and maintains its spin period with the stability of the best mechanical clocks. These objects were named pulsars, pulsating radio sources. The first were all radio pulsars, but subsequent discoveries extended the category to X-ray pulsars, gamma-ray pulsars, and optical pulsars. The principal pulsar catalog now contains more than 4,000 objects, and they have become one of the most scientifically productive classes of astronomical objects in the cosmos. Hewish received the Nobel Prize in Physics in 1974 for the discovery of pulsars, shared with Martin Ryle for his work on aperture synthesis in radio astronomy. The omission of Jocelyn Bell Burnell from the Nobel Award was widely criticized and remains one of the best-known debates about recognition in modern science. Bell Burnell herself has often spoken with generosity about the collaborative nature of the work, but the historical record is clear that her careful attention to the chart data was essential to the discovery. The discovery of pulsars also changed how astronomers thought about small signals. Before 1967, radio astronomy was already revealing a universe invisible to optical telescopes, but the idea of a source producing narrow, clock-like pulses was unexpected. The Cambridge array used by Jocelyn Bell Burnell and Anthony Hewish had been designed to study interplanetary scintillation, the rapid flickering of compact radio sources caused by the solar wind. Pulsars appeared in the data because their signals had precisely the kind of rapid variation the instrument could register. Bell Burnell's task required persistence. The telescope produced long paper records, and the first pulsar did not appear as a dramatic image. It appeared as a small patch of unusual trace, what she later described as a bit of scruff. The signal disappeared and returned. Equipment faults, terrestrial interference, and reflections from human technology had to be considered. The source followed sidereal time rather than ordinary solar time, meaning it returned according to the rotation of the celestial sphere. That was a powerful sign that it came from beyond Earth. The first source is now known as CP 1919 or PS or B 1919 plus 21. Its period was about 1.33 seconds. When additional pulsars were found, the idea of a single artificial transmitter became implausible. The regularity remained astonishing, but it now demanded an astrophysical mechanism. Several compact object ideas were discussed. A pulsating white dwarf could not easily explain the fastest periods. A rotating neutron star could. A neutron star only tens of kilometers across could spin once per second or even many times per second without flying apart. If its magnetic axis were tilted relative to its rotation axis, radiation beams tied to the magnetic poles would sweep across the sky. The lighthouse model transformed an apparently pulsing source into a rotating one. The distinction matters. The neutron star is not usually brightening and fading as a whole. Our line of sight intersects a beam. Many neutron stars may produce beams that never cross Earth, so the observed pulsar population is only a geometrically selected fraction of the true population. Some have one visible pulse per rotation. Others show two or more components because of complex beam structure or because radiation from both magnetic poles becomes visible. The discovery immediately suggested new tests. If pulsars were rotating neutron stars, their periods should change as they lose energy. That spin down was observed. Young pulsars generally slow more rapidly than old millisecond pulsars. The period and its rate of change became basic observables from which astronomers estimate magnetic field strength, characteristic age, and spin-down power. These derived quantities are useful, but not exact biographies. The characteristic age assumes a particular breaking law and an initial spin period much shorter than the present one. Neither assumption is always valid. A pulsar's inferred magnetic field depends on a simplified rotating dipole model. Real magnetospheres contain plasma, currents, and changing geometry. Still, a simple measurement of pulse period and period derivative can place a pulsar within a broad evolutionary family. A diagram of pulsar period against period derivative reveals several populations. Young energetic pulsars occupy one region. Magnetars sit at long periods and large spin-down rates. Millisecond pulsars gather at very short periods and tiny period derivatives. Lines on the diagram represent approximate magnetic fields, characteristic ages, and spin-down luminosities. The arrangement is not merely descriptive. It records different histories of birth, magnetic evolution, and binary interaction. Pulsar signals also carry information about the space between the star and Earth. Radio waves of lower frequency travel slightly more slowly through ionized interstellar plasma than higher frequency waves. A sharp pulse therefore arrives first at high radio frequencies and later at low frequencies. The amount of delay gives the dispersion measure, which is the integrated density of free electrons along the line of sight. Dispersion measure helps estimate distance when combined with models of the Milky Way's electron distribution. The estimates can be uncertain, especially along complex directions through spiral arms, but pulsars themselves become probes of galactic plasma. Their signals reveal turbulence, scattering, magnetic fields, and structures that may be otherwise difficult to map. Polarization adds another layer. Charged particles radiating in a strong magnetic field produce highly polarized radio emission. As a pulsar rotates, the angle of linear polarization may sweep across the pulse in a pattern related to the orientation of the magnetic and rotation axis. Faraday rotation along the path to Earth twists the polarization by an amount that depends on wavelength and on the interstellar magnetic field. Combining rotation measure with dispersion measure gives an estimate of the average magnetic field along the line of sight. The first pulsar discovery therefore opened several fields at once. It confirmed neutron stars. It created a new way to test gravity. It provided clocks scattered across the galaxy. It offered narrow beams for studying interstellar matter. It exposed the physics of relativistic magnetospheres. It also demonstrated that discoveries can hide in data produced for a different purpose. Belle Burnell's later career became inseparable from the story, but her contribution extends beyond the question of the Nobel Prize. She has repeatedly used the attention surrounding the discovery to support younger scientists and people from underrepresented backgrounds. In 2018, when she received the Special Breakthrough Prize in Fundamental Physics, she donated the award money to help students from groups underrepresented in physics. The gesture connected the history of one overlooked graduate student to opportunities for future researchers. Pulsar astronomy has continued to reward patients of the same kind. Surveys record immense volumes of data contaminated by human radio interference. Search algorithms test many possible dispersion measures and acceleration patterns. Machine learning systems help sort candidates, but human judgment still matters. Some pulsars appear intermittently. Some null for minutes or days. Some emit isolated bursts rather than a continuous train of pulses. A source can remain hidden because its binary acceleration smears its signal or because interstellar scattering broadens its pulses. The catalog is therefore not a completed inventory. It is a changing map of what present instruments and methods can detect. The more than 4,000 catalog pulsars represent only a small visible sample of a galactic population that may number hundreds of millions. Each new survey reaches fainter sources, faster binaries, more distant regions, and lower radio frequencies. The original bit of scruff has become an entire astronomy of precision signals. The structure of a neutron star is extraordinary because its layers represent different physical regimes, each operating under conditions for which the physics is partly understood and partly uncertain. The outermost layer of a neutron star, the atmosphere, is a thin film of plasma perhaps a centimeter thick, containing hydrogen, helium, and heavier elements. Despite being extremely thin, this atmosphere lies in a surface gravitational field roughly 100 billion times stronger than Earth's. Large topographic features cannot survive there. The crust may support tiny deformations, but on the scale of a star, the surface is extraordinarily close to spherical. Below the thin atmosphere is the outer crust, composed of a crystal lattice of nuclei embedded in a sea of mobile electrons. Iron may dominate near the surface of a young, non-accreting neutron star, but deeper layers contain progressively more neutron-rich nuclei as pressure rises. The physics of the outer crust is relatively well understood, being nuclear physics under conditions achievable in principle, if not in practice, in terrestrial laboratories. Below the outer crust is the inner crust. Together, the outer and inner crust are usually only about 1 kilometer thick, though the exact value depends on the star's mass and the equation of state. In the inner crust, the density increases to the point that free neutrons begin to appear, neutrons that have leaked out of the nuclei and fill the space between them. This region of the inner crust may host exotic phases of nuclear matter that have no terrestrial analog, the pasta phases, named after food for their shapes. As density increases through the inner crust, the nuclear matter transitions from individual spherical nuclei to cylindrical rods of nuclear material, spaghetti, to flat sheets, lasagna, to cylindrical holes in dense nuclear matter, sometimes called anti-spaghetti, and finally to roughly spherical bubbles, sometimes called anti-gnocchi or Swiss cheese phases. These pasta phases are predicted by nuclear theory, but have never been directly observed. The physics occurs at densities achievable only inside neutron stars. Below the inner crust is the outer core, where nuclear clusters dissolve into nearly uniform matter at roughly 1/3 to 1/2 of nuclear saturation density. Farther inward, the density reaches and then exceeds nuclear saturation density, about 2.7 times 10 to the 17th kilograms per cubic meter, with the precise reference value depending on convention. Individual nuclei no longer exist there. The material is a fluid dominated by neutrons, with smaller populations of protons, electrons, and, at sufficient density, muons. The outer core is thought to be a quantum fluid, specifically a superfluid of neutrons, in which the neutrons pair up in a manner analogous to the Cooper pairs of superconductors and flow without viscosity. The protons in the outer core may be superconducting in the same sense, flowing without electrical resistance. The combination of neutron superfluidity and proton superconductivity produces a material with properties unlike anything in ordinary physics. The inner core, the innermost region of the most massive neutron stars, is the most uncertain. At the extreme densities prevailing there, something other than neutrons may be the dominant constituent. Several exotic possibilities have been proposed. Hyperons, particles containing one or more strange quarks, heavier relatives of the proton and neutron, might form as the density rises beyond the point where their formation is energetically favorable. Kaon condensates, a superfluid-like state of particles called kaons, might form. And at the extreme, the density might be high enough that quarks are no longer confined within individual nucleons, but form a cold, dense phase of deconfined quark matter. This would differ from the extremely hot quark gluon plasma produced for fleeting moments in high-energy particle collisions. The presence or absence of these exotic inner core states directly affects the maximum mass of a neutron star. Hyperons and kaon condensates tend to soften the equation of state, making it more compressible, which would lower the maximum mass. A stiffer equation of state generally supports a larger maximum mass, while a softer one reaches gravitational instability at a lower mass. The discovery of neutron stars with well-measured masses close to or exceeding 2 solar masses has been important for constraining the equation of state, because it establishes that whatever is in the core, it must be stiff enough to support at least that mass. PS our J0740 plus 6620 has a precisely measured mass of about 2.08 solar masses. The Black Widow pulsar PS RJ0952-0607 has been estimated at about 2.35 solar masses, with an uncertainty of roughly 1/10 of a solar mass in the latest analysis, although modeling systematics remain. Objects like these establish that any successful equation of state must support neutron stars of at least about 2 solar masses, and perhaps substantially more. The layered picture of a neutron star is an attempt to describe matter over an extraordinary range of density. The density at the top of the atmosphere may be lower than the density of air on Earth, while the central density can be several times that of an atomic nucleus. Moving inward by only a few kilometers crosses physical regimes that, in ordinary astronomy, might be separated by entire stars. The atmosphere determines the spectrum that escapes. Even when it contains very little mass, it changes how radiation is absorbed and re-emitted. A hydrogen atmosphere can make the star appear hotter or larger than a simple blackbody fit would suggest. Helium, carbon, or heavier element atmospheres produce different spectral features. Strong magnetic fields divide atomic energy levels and make opacity depend on direction and polarization. Below the atmosphere may be a condensed surface, especially in strongly magnetized and relatively cool stars. Whether the outermost material behaves as gas, liquid, or solid depends on temperature, field strength, and composition. Accretion can replace the original surface material with hydrogen and helium from a companion or with heavier ashes left after thermonuclear burning. The outer crust begins at low enough density that nuclei remain distinct. Pressure ionises atoms completely. Electrons are no longer attached to individual nuclei and move through the lattice as a degenerate gas. With increasing depth, the most energetically favored nuclei become richer in neutrons. Electron capture converts protons to neutrons, lowering the nuclear charge. At a density of roughly 400 million kilograms per cubic centimeter, depending on the nuclear model, the nuclei become so neutron-rich that additional neutrons are no longer bound inside them. This is neutron drip. Free neutrons begin to occupy the space between nuclear clusters. The inner crust starts. The phrase free neutron does not mean a neutron moving independently as it would in empty space. The particles form a dense quantum system and interact strongly with the lattice and with one another. At sufficiently low temperature, they are expected to pair and form a superfluid. The lattice itself is immersed in electrons and superfluid neutrons, creating a material that is simultaneously crystalline and quantum fluid-like. Near the base of the crust, competition between the attractive nuclear force and repulsive electric force may frustrate the matter. Nuclear attraction tries to gather nucleons together, while the positively charged protons resist being concentrated into large structures. The compromise can produce rods, sheets, tubes, and bubbles. These are the nuclear pasta phases. The food names are memorable, but the physics is serious. Pasta may influence electrical conductivity, heat flow, neutrino emission, magnetic field evolution, and the way the crust breaks. Some simulations suggest that tangled pasta could be highly resistant to shear. Other calculations find that defects and disorder may scatter electrons and alter the long-term cooling of old neutron stars. No telescope can photograph a piece of nuclear pasta. Evidence must come indirectly. The cooling curve of an accreting neutron star after an outburst can reveal how quickly heat travels through the crust. The frequencies of oscillations during magnetar flares may depend on the crust's elasticity. Pulsar glitches constrain how superfluid neutrons exchange angular momentum with the lattice. Each observation tests a different aspect of the same hidden layer. At the crust-core transition, the clusters dissolve into nearly uniform matter. Neutrons dominate, but a small fraction of protons and electrons is essential. Charge neutrality requires positive and negative charge to balance. Muons may also appear once the electron chemical potential becomes high enough to create them. The composition is set by beta equilibrium, a balance maintained by weak interactions among neutrons, protons, electrons, and other particles. The term neutron matter can therefore be misleading if taken too literally. A stable neutron star is not one giant atomic nucleus made of neutrons alone. Its matter is gravitationally bound, electrically neutral on large scales, and stratified. The fraction of protons may be only a few percent in parts of the core, but those protons affect cooling, superconductivity, magnetic flux, and the allowed nuclear reactions. One important cooling channel is the direct Urca process. A neutron can transform into a proton, electron, and antineutrino, while the reverse reaction restores the neutron and emits a neutrino. Momentum conservation permits this rapid cycle only when the proton fraction exceeds a threshold that depends on the equation of state and the other particles present. If direct Urca operates in a sufficiently large part of the core, the star can cool much faster than through the slower modified Urca process. The name Urca came from physicists George Gamow and Mario Skinberg, who compared the rapid disappearance of energy through neutrinos to money disappearing at a casino in Rio de Janeiro. The playful name now labels some of the most important reactions in compact star cooling. At greater density, the uncertainty becomes fundamental. Nuclear experiments constrain interactions near the density of ordinary nuclei. Theory can extend those constraints to somewhat higher density, but eventually different models diverge. One predicts relatively high pressure and a larger radius. Another predicts lower pressure and a smaller star. Some allow new particles to appear. Others predict a transition to deconfined quark matter. Hyperons are baryons that contain strange quarks. At high density, converting some energetic neutrons into hyperons may lower the total energy. But the appearance of hyperons often reduces pressure, making it difficult for the model to support neutron stars above 2 solar masses. This tension is known as the hyperon puzzle. Additional repulsive interactions among hyperons may solve it, but those interactions are poorly constrained. A phase transition to quark matter could also soften the equation of state, but not always in a simple way. Strongly interacting quark matter may become stiff again at higher density. Some models produce hybrid stars with a hadronic outer core and a quark matter inner core. Others allow a separate branch of stable compact stars with nearly the same mass as ordinary neutron stars, but different radii, sometimes called twin stars. Observations have not confirmed such a branch. A sharp phase transition might leave clues in mass radius measurements, merger waveforms, post-merger oscillations, or the distribution of neutron star masses. The absence of an obvious clue does not yet rule it out. Current data sample only a small number of stars with useful precision. The equation of state also determines the moment of inertia, the relation between mass and spin. In a binary pulsar, relativistic timing may eventually measure the moment of inertia of one neutron star. That would add a new kind of constraint, because two equations of state that predict similar radii can predict different internal mass distributions. Another useful quantity is the Love number, named for the mathematician Augustus Edward Hopf Love. It describes how an object deforms under a tidal field. The tidal deformability measured in a merger combines the Love number with a strong dependence on radius. A slightly larger neutron star is much easier to deform. That is why the final few orbits of a binary can reveal dimensions of objects more than 100 million light-years away. The search for the equation of state is not likely to end with one decisive observation. It resembles the reconstruction of a hidden object from many shadows. Massive pulsars establish a lower bound on supportable mass. NICER provides mass radius regions. Gravitational waves measure tidal response. Nuclear experiments constrain matter near saturation density. Cooling curves test neutrino processes and superfluid gaps. Glitches probe angular momentum reservoirs. Each shadow removes some possibilities. As the allowed region narrows, the remaining differences become more physically meaningful. A radius near 11 kilometers and a radius near 13 kilometers may sound similar, yet they imply substantially different pressures in the core. A maximum mass of 2.2 solar masses and one of 2.5 solar masses would lead to different outcomes after mergers. A remnant that survives for milliseconds behaves differently from one that survives for seconds, minutes, or indefinitely. The deepest core may contain only a few tenths of the star's radius, but it determines the boundary between a neutron star and a black hole. It may also determine whether nature produces a new state of matter that cannot exist anywhere else for more than a fraction of a second. The entire object is a laboratory, but the innermost kilometers are the part of the laboratory whose contents remain behind the thickest wall. Pulsars are the most observationally productive type of neutron star, and the range of phenomena they exhibit is remarkable. A pulsar's radio emission is produced by the acceleration of charged particles along the magnetic field lines near the magnetic poles of the rapidly rotating neutron star. As the star rotates, the magnetic poles sweep through space, and the beams of radio emission they produce sweep like lighthouse beams. When the geometry aligns so that a beam crosses Earth's line of sight, we detect a pulse for every rotation of the star. The pulse period, the time between successive pulses, is the rotation period of the star, and it is extraordinarily stable. The best millisecond pulsars, those spinning hundreds of times per second, can rival the long-term regularity of the most stable human-made clocks, although atomic clocks are generally superior over shorter intervals. This extraordinary stability has made pulsars powerful tools for fundamental physics. The region above the surface is as important as the material below it. A rotating magnetar conductor generates electric fields. Near a neutron star, those fields can be strong enough to pull charged particles from the surface and accelerate them to relativistic energies. The space around an active pulsar is therefore not an empty vacuum. It is a magnetosphere filled with electrons, positrons, ions, currents, and intense radiation. The magnetic field is often drawn as a simple dipole, like the field around a bar magnet. Real pulsars are more complicated. Close to the surface, higher-order magnetic structures may be important. Farther out, rotation twists the field and forces some lines open. The distance at which rigid corotation would require the speed of light is called the light cylinder. Inside it, much of the plasma attempts to rotate with the star. Beyond it, field lines cannot remain closed in the same way, and a wind flows outward. The magnetic poles need not coincide with the rotation poles. Along open field lines near the magnetic poles, charged particles can escape. Electric potential differences accelerate them. Curved trajectories cause them to emit curvature radiation. High-energy photons interact with the magnetic field or with other photons and create electron-positron pairs. These secondary particles produce further radiation and pair cascades. The radio emission mechanism remains one of the major unsolved problems in pulsar physics. Astronomers understand the broad energy source and magnetic geometry, but the exact coherent process that converts particle motion into extraordinarily bright radio waves is still debated. Ordinary incoherent radiation from independent particles would be far too weak. The particles must radiate in a coordinated way. This unresolved mechanism is reflected in the variety of pulse behavior. Individual pulses can vary dramatically even when the average profile is stable. Some pulsars show drifting subpulses that move systematically across the pulse window. Some switch between distinct emission modes. Some stop emitting detectable radio pulses for seconds, hours, or longer, a behavior called nulling. A few objects change not only their radio emission, but also their spin-down rate. When the magnetosphere switches state, the current system and torque on the star change. The pulsar then slows at a measurably different rate. This shows that the magnetosphere is a dynamic electrical circuit coupled to the rotation of the entire star. Rotating radio transients, or RRATS, reveal themselves mainly through isolated radio bursts separated by long quiet intervals. They may be extreme nulling pulsars, old objects near the end of their radio-emitting lives, or a collection containing more than one physical class. Their discovery reminded astronomers that periodicity searches can miss sources whose emission is too intermittent. At the opposite extreme are giant pulses. The Crab pulsar occasionally produces individual radio pulses hundreds or thousands of times brighter than its average pulse. Some last only nanoseconds in substructure. The inferred brightness temperature is so high that it cannot represent ordinary thermal emission. Giant pulses are also seen from a small number of millisecond pulsars and appear to be connected with particular high-energy emission regions. Pulsars emit beyond radio wavelengths. Young energetic pulsars can be bright in X-rays and gamma rays. The Fermi Gamma Ray Space Telescope has discovered many gamma-ray pulsars, including radio-quiet objects whose radio beams do not cross Earth or whose radio emission is too faint to detect. Gamma-ray photons are thought to come from particle acceleration in the outer magnetosphere, perhaps near gaps in the charge distribution or in current sheets beyond the light cylinder. The pulse peaks at different wavelengths do not always align. Radio emission may arise relatively close to the magnetic poles, while gamma rays come from higher altitudes. Comparing their phases helps reconstruct the three-dimensional geometry. Polarization measurements add further constraints. The pulsar wind carries away energy and angular momentum in particles and electromagnetic fields. Near the star, the wind may be dominated by magnetic energy. Farther out, a large fraction must be converted into particle kinetic energy to explain pulsar wind nebulae. How that conversion occurs is called the sigma problem, named for the parameter describing the ratio of electromagnetic to particle energy. Current sheets in the wind may reconnect, turning magnetic energy into heat and particle acceleration. At the termination shock, the wind is abruptly slowed by surrounding material. Particles are accelerated to energies far beyond those achieved in ordinary laboratory settings. Their synchrotron and inverse Compton radiation makes the invisible wind visible. The shape of a pulsar wind nebula depends on the surrounding medium. A young pulsar inside its supernova remnant may inflate or roughly bubble-like nebula. A fast-moving pulsar that has escaped its remnant can create a bow shock, with a long tail trailing behind it. Some of these structures extend for light years and point backward along the neutron-star's path. One remarkable example is the Guitar Nebula, produced by a high-velocity pulsar moving through interstellar gas. Its bow shock and narrow wake create a shape resembling the body and neck of a guitar. The visible structure is not the neutron star itself, but hydrogen gas excited by the shock. Other pulsars produce long X-ray tails that may trace particles escaping along magnetic field lines in the surrounding interstellar medium. These objects allow astronomers to study plasma physics over scales impossible to reproduce on Earth, with a compact engine only kilometers wide creating structures many light years long. The rotational energy reservoir is finite. As a pulsar slows, its ability to create pair cascades and coherent radio emission may weaken. On the period-period derivative diagram, a region called the death line marks where simple models predict that radio emission becomes difficult to sustain. The boundary is not sharp. Some pulsars emit beyond it, and some stop earlier. Magnetic geometry, surface temperature, and plasma supply all matter. A radio pulsar can therefore disappear without the neutron star disappearing. The beam may move away from our line of sight through precession. The emission may become intermittent. The star may cross into a state where pair production no longer supports radio beams. It then joins the enormous hidden population of quiet neutron stars. Even while visible, a pulsar is selective in what it tells us. We observe the beam, not the whole magnetosphere. We infer the magnetic field from spin down, not from touching the surface. We reconstruct the wind from a nebula shaped by its environment. Yet the precision and variety of these signals make the reconstruction possible. A neutron star only a few tens of kilometers wide can write its rotation into radio waves detectable across much of the galaxy. The precision of pulsar timing, the measurement of exact pulse arrival times to a precision of microseconds or better, allows the detection of tiny deviations from a perfectly uniform rotation rate. These deviations can be produced by several effects. The orbital motion of the pulsar around a companion produces a regular pattern of Doppler shifts. The pulsar emits pulses slightly faster when moving toward us in its orbit and slightly slower when moving away, the equivalent of the Doppler shift in sound from a moving source. By modeling this pattern, the orbital parameters of the binary system can be determined, and from the orbital parameters, the masses of both the pulsar and its companion. The binary pulsar PSR 1913 plus 16, discovered by Russell Hulse and Joseph Taylor in 1974, provided the first indirect evidence for gravitational waves. The two neutron stars in this system are orbiting each other with a period of about 7.5 hours and are separated by only a few times the Earth-Moon distance, far closer than ordinary stars in a typical binary system. Einstein's general relativity predicts that such a system should radiate gravitational waves, ripples in space-time, as the two masses accelerate through their orbit, and this radiation should carry away orbital energy, causing the orbital period to decrease as the stars spiral closer together. Hulse and Taylor measured the orbital period of PSR 1913 plus 16 precisely over more than a decade, and found that it was indeed decreasing at exactly the rate predicted by general relativity for a system losing energy to gravitational wave radiation. After corrections for the motion of the system through the galaxy, the agreement between the observed orbital decay and the general relativistic prediction is within a fraction of a percent, one of the most precise confirmations of any prediction in physics. Hulse and Taylor received the Nobel Prize in Physics in 1993 for this work, the second Nobel Prize with a connection to pulsar research. The binary pulsar system demonstrated that gravitational waves exist and carry energy, a confirmation of general relativity's prediction that required no direct detection of the waves themselves. The direct detection would wait until 2015, when LIGO detected gravitational waves from a binary black hole merger, but the Hulse-Taylor system had already established that gravitational waves were real. Binary pulsars turn that precision into a test of gravity because each pulse travels through a changing spacetime. The observed arrival time includes many delays. Earth moves around the Sun. The pulsar moves through the galaxy. The signal crosses ionized plasma. In a binary, the pulsar changes its distance from us during every orbit. Relativistic time dilation and gravitational redshift alter the clock rate. The companion's gravitational field delays the signal through the Shapiro effect. A timing model accounts for all of these influences. When observations are precise enough, tiny residual differences between measured and predicted arrival times reveal new physics or imperfect assumptions. The model may contain the pulsar's position, proper motion, parallax, spin frequency, spin down, dispersion measure, orbital period, eccentricity, projected orbit size, and several post-Keplerian relativistic parameters. In general relativity, different post-Keplerian parameters depend on the two stellar masses in different ways. Measuring two of them can determine both masses. Measuring three or more over-constrains the system and tests the theory. If all measurements intersect at the same pair of masses, general relativity passes a strong internal consistency test. The Hulse-Taylor pulsar was the first great example, but later systems became even more powerful. The double pulsar, PSR J0737-3039A and B, discovered in 2003, is the only known system in which both neutron stars have been observed as radio pulsars. One rotates about 44 times per second, while the other rotates once every 2.8 seconds. They orbit each other in about 2.4 hours. The orbit is seen nearly edge-on, making the Shapiro delay especially clear. The system displays relativistic periastron advance, gravitational redshift, time dilation, orbital decay, and changes in pulse geometry caused by relativistic spin precession. Because both stars are detectable, the ratio of their projected orbital sizes gives a mass ratio with little dependence on a particular theory of gravity. Long-term timing of the double pulsar has tested general relativity to remarkable precision. Its orbital period shortens as gravitational waves carry energy away. The result agrees with Einstein's theory after accounting for the system's motion and galactic acceleration. It also includes higher-order effects that were once far beyond observational reach. Relativistic spin precession gradually changes the direction of a pulsar's spin axis relative to Earth. The beam can drift through our line of sight and alter its profile. Pulsar B in the double pulsar disappeared from view in 2008, probably because precession moved its beam away. Models predict that it may return as the geometry continues to change. Binary pulsars can also test the equivalence principle and possible alternatives to general relativity. Some theories predict dipolar gravitational radiation, additional to the quadrupolar radiation of general relativity. A neutron star paired with a white dwarf is especially useful because the two bodies have very different gravitational binding energies. Precise orbital decay measurements limit how strongly such dipolar radiation can occur. Triple systems offer another opportunity. PSRJ0337 plus 1715 is a millisecond pulsar with two white dwarf companions in a hierarchical triple. The inner pulsar white dwarf pair falls through the gravitational field of the outer white dwarf. If strongly self-gravitating bodies responded differently from weakly bound objects, the pulsar's motion would reveal it. Timing observations have placed stringent limits on such violations of the strong equivalence principle. Pulsars in orbit around black holes would be even more powerful. A pulsar circling a stellar mass black hole could measure the black hole's mass and spin with high precision. A pulsar close to the supermassive black hole at the center of the Milky Way could test space-time in a far stronger gravitational field. Searches continue, but scattering and the complex environment near the galactic center make ordinary radio pulsars difficult to detect at many frequencies. The discovery of magnetars near the galactic center shows that neutron stars do exist there. Higher frequency radio searches reduce the effect of scattering. Future instruments may find a suitable pulsar in a compact orbit around Sagittarius A star. Such a system could test whether the black hole's quadrupole moment matches the prediction for a Kerr black hole. Binary evolution is what creates many of the most precise pulsars. A neutron star born first may spend millions of years orbiting a normal companion. When the companion expands, gas flows through an accretion disk. The transfer spins the neutron star up and reduces the observable magnetic field. Later, the companion may become a white dwarf. The result is a millisecond pulsar with a stable orbit and exceptionally regular pulses. If the companion is massive enough to undergo its own core collapse, the second supernova can create a double neutron star system. Survival requires favorable mass loss and kick direction. The orbit may become eccentric. The firstborn neutron star is usually recycled and spins rapidly, while the second-born object is younger and spins more slowly. The future merger time depends strongly on separation and eccentricity. Gravitational wave power rises steeply as the objects approach. A wide pair can survive longer than the age of the universe. A tight pair may merge within millions or billions of years. Observed double neutron star systems allow astronomers to estimate the merger rate that gravitational wave observatories should detect. Pulsar masses also record evolutionary history. Neutron stars born in core collapse often cluster around characteristic masses, but there is a broad distribution. Recycled pulsars can gain matter. Some accrete only a small amount, enough to spin them up. Others in long-lived systems may gain several tenths of a solar mass. Black Widow and Redback systems can contain especially massive pulsars, although measuring their masses requires modeling a companion whose atmosphere is strongly heated on one side. A binary can become a laboratory because orbital mechanics is clean. Two compact masses moving in near vacuum can be described with extraordinary precision. Yet the formation path is messy. Mass transfer, common envelopes, supernova kicks, magnetic braking, and stellar winds. The final clock-like system is the product of a long and unstable history. That contrast is common in neutron-star astronomy. The object may have been born in an asymmetric explosion, accelerated through a turbulent remnant, and transformed by years of accretion. Afterward, its pulses can arrive with such consistency that deviations of microseconds expose the curvature of spacetime. Millisecond pulsars spinning hundreds of times per second, are thought to have been spun up by accretion of material from a companion star in a binary system. The process, called recycling, involves the companion star expanding as it ages, spilling material onto the neutron star through an accretion disk. The infalling material carries angular momentum and gradually spins the neutron star up to very fast rotation rates over millions of years of accretion. The fastest known pulsar, PSRJ 1748-2446 AD, rotates at 716 times per second, with a period of about 1.4 milliseconds. Its pulse repetition rate lies in the audible frequency range, although the electromagnetic waves themselves are radio waves. The stability of millisecond pulsars as timekeepers has been harnessed for gravitational wave detection in a very different way from LIGO. Pulsar timing arrays, consortia of observatories monitoring dozens to hundreds of millisecond pulsars simultaneously, use the network of precision clocks distributed across the galaxy to search for the correlated timing residuals that would be produced if a low-frequency gravitational wave passed through the solar system. A gravitational wave stretches and compresses space as it passes, slightly changing the distance between Earth and each pulsar, and therefore slightly shifting the observed pulse arrival times. By correlating the timing residuals from many pulsars across the sky, the distinctive signature of a background of gravitational waves can be separated from noise. In 2023, the major pulsar timing array collaborations, NA&OGrav in North America, EPTA in Europe, PPTA in Australia, and CPTA in China, announced strong evidence for a gravitational wave background, a diffuse bath of low-frequency gravitational waves from an unresolved population of sources. The most likely source is a cosmic population of binary supermassive black holes, pairs of supermassive black holes at the centers of merged galaxies, orbiting each other at close range and radiating low-frequency gravitational waves as they gradually spiral inward. The detection of this background opens a new observational window onto the population of supermassive black holes across cosmic history, complementary to the higher frequency binary stellar mass black hole and neutron-star mergers detected by LIGO. The word recycled describes more than fast rotation. Accretion can transform nearly every observable property of a neutron star. The old star is heated. Its surface composition changes. Its magnetic field may become weaker or more deeply buried. The spin period falls from seconds to milliseconds. When mass transfer ends, the system can emerge as a radio millisecond pulsar whose rotational age appears much younger than the true age of the neutron star. Many millisecond pulsars have white dwarf companions, the exposed cores of stars that donated their envelopes. The mass and composition of the white dwarf reveal the evolutionary channel. A helium white dwarf often points to long-lived mass transfer from a low-mass star. A carbon-oxygen white dwarf suggests a more massive donor and a different history. Some systems have nearly destroyed their companions. Black widow pulsars orbit companions with extremely low masses. The pulsar irradiates and ablates the companion, driving material away. Redback pulsars have heavier, non-degenerate companions and can switch between a radio pulsar state and an accreting X-ray state. These transitional millisecond pulsars provide rare views of the moment when accretion begins or ends. In one state, a disk reaches toward the neutron star and produces X-rays. In another, The radio pulsar turns on, and its wind pushes material outward. Some systems switch on human timescales, showing that the boundary between an accretion-powered pulsar and a rotation-powered pulsar is not an irreversible evolutionary step. The fastest known pulsar, PSRJ 1748-2446 AD, lies in the globular cluster Terzan 5. It rotates 716 times per second. Globular clusters are especially rich in millisecond pulsars because their crowded cores promote close stellar encounters. A neutron star can exchange into a binary, acquire a new companion, and begin another episode of mass transfer. This means a pulsar's present companion may not be the star with which it was born. In a dense cluster, binaries are repeatedly rearranged. Neutron stars can participate in encounters, collisions, and exchanges over billions of years. The resulting systems include unusual eccentric binaries and pulsars with companions that would be difficult to produce through isolated binary evolution. Millisecond pulsars are stable because they have weak external torques and large rotational inertia, yet their apparent regularity is not perfect. The interstellar medium changes. Planets or asteroid belts could perturb a pulsar. The solar system's ephemeris can introduce correlated timing errors. Clock errors at observatories can affect every source. Pulsar timing arrays must separate all of these from the pattern expected from gravitational waves. A nanohertz gravitational wave has a period of years to decades. No instrument can build arms millions of light years long, but a pulsar timing array effectively uses Earth and distant pulsars as endpoints. The pulses left each neutron star hundreds or thousands of years ago. Their arrival times today are compared with a model. A passing gravitational wave changes the space-time metric and creates a characteristic correlation between residuals from different directions on the sky. That angular correlation is called the Helling-Downs curve. Pulsars separated by one angle should show a different average correlation from pulsars separated by another. Evidence for this pattern, together with a common red noise process, led several timing array collaborations in 2023 to report strong evidence for a nanohertz gravitational wave background. The most likely explanation is a cosmic population of supermassive black hole binaries. When galaxies merge, their central black holes can form pairs. At separations of light years or less, interactions with stars and gas may shrink the orbit. Eventually, gravitational radiation becomes dominant. The combined signal from many unresolved binaries forms a background. The measured background can therefore reveal how often galaxies merge, how black holes grow, and how efficiently binaries cross the difficult range of separations between galactic scales and the gravitational wave regime. Alternative contributions, including primordial gravitational waves or cosmic strings, are also studied, but astrophysical black hole binaries are the leading expectation. As timing baselines grow, the arrays may separate individual nearby binaries from the background. The signal would not appear as a brief event. It would be a slowly evolving pattern over years. Electromagnetic observations might identify a galaxy containing the source, creating a form of multi-messenger astronomy at frequencies far below those observed by ground-based interferometers. Pulsars can also serve as navigation beacons. NASA's Sextant experiment used NICER to demonstrate autonomous navigation with X-ray pulsars. A spacecraft can compare observed pulse arrival times with predicted ones and infer its position, much as a receiver uses signals from navigation satellites around Earth. The accuracy is not yet comparable with local spacecraft tracking for every purpose, but the concept could provide independent navigation far from Earth. The metaphor of a galactic positioning system is useful with one qualification. Pulsars are not transmitters built for us. Their positions, spin evolution, binary motion, and timing noise must be modeled. X-ray detectors need sufficient collecting area. Yet the fact that natural objects thousands of light years away can guide a spacecraft is a remarkable consequence of rotational stability. A millisecond pulsar may have begun as an ordinary young neutron star billions of years ago. It may have crossed a supernova remnant, lived quietly, entered mass transfer, accreted matter, spun up, and emerged as a precision beacon. The pulses we receive now are the final expression of that entire history. Pulsars also produced another unexpected discovery: the first confirmed planets beyond the solar system. In 1992, timing observations of the millisecond pulsar PS RB 1257+12 revealed small periodic variations that could not be explained by the pulsar's rotation alone. The pattern came from the gravitational pull of orbiting planets. These worlds circle a neutron star about 1,000 light years away. Their existence was surprising because the supernova that created the pulsar should have disrupted or destroyed any original planetary system nearby. The planets may have formed later from a disk of material left by fallback, produced by the destruction of a companion, or assembled during a later phase of binary evolution. Pulsar timing is exceptionally sensitive to planetary masses. A planet pulls the neutron star around the common center of mass. That motion changes the distance traveled by every pulse. The timing shift can reveal objects much smaller than those detectable around ordinary stars by many other methods. The pulsar planets are not likely to resemble Earth in habitability. They are exposed to high-energy particles and radiation from the neutron star. Their sky is illuminated by a compact object rather than a normal sun. Yet they demonstrated that planet formation can occur under conditions once considered almost impossible. The discovery also contained a cautionary story. A year earlier, another team announced a planet around a different pulsar, but the signal came from an error in accounting for Earth's orbit. The claim was publicly withdrawn. Soon afterward, the real system around PS RB 1257+12 was confirmed. Precision timing can reveal tiny effects, but it also requires every motion of Earth and the solar system to be modeled correctly. Later searches found additional candidate or confirmed companions around neutron stars, including objects that blur the boundary between planets, brown dwarfs, and stripped stellar remnants. They are rare compared with pulsar binaries, but they expand the range of environments in which organized systems can form. A neutron star can therefore be both a stellar remnant and the center of a new system. The original star's planets may be lost, while a second generation forms from debris. Destruction and formation are separated not by different regions of space, but by different chapters in the history of the same object. Among the most extreme neutron stars are the magnetars, a class with magnetic fields so intense that they are incomprehensible by ordinary physical standards. A typical pulsar has a surface magnetic field of roughly 10 to the 12th Gauss, 10 to the 12 times the strength of Earth's magnetic field. Earth's field is about half a Gauss. A bar magnet might produce a field of 100 Gauss. MRI machines use fields of a few tens of thousands of Gauss. The most powerful electromagnets in laboratories reach a few million Gauss. A typical pulsar exceeds all of these by factors of millions. A magnetar can have a surface magnetic field of roughly 10 to the 14th to 10 to the 15 Gauss. That is roughly 100 to 1,000 times stronger than the field of a typical young radio pulsar, and hundreds of trillions to a few quadrillion times stronger than Earth's surface field. At these field strengths, the magnetic energy stored in the magnetar's field is greater than its rotational kinetic energy, a situation reversed from most pulsars, where rotation drives the magnetic activity. The magnetar's field alters the behavior of the quantum vacuum around the star. Above the quantum electrodynamic critical scale of about 4.4 times 10 to the 13th Gauss, effects such as vacuum birefringence, and unusual photon conversion processes become important. The field also changes atomic structure, squeezing electron clouds into elongated forms along the magnetic field and producing chemistry unlike anything familiar on Earth. Magnetars reveal themselves through spectacular outbursts. The twisted magnetic field of a magnetar can suddenly reconfigure, a starquake, in which the crust of the neutron star cracks under the magnetic stress and the field snaps to a new configuration, releasing enormous amounts of energy in milliseconds. These giant flares can release, in a fraction of a second, more energy than the sun radiates in 100,000 years, observable from thousands of light years away as brief, intense bursts of soft gamma-ray radiation. The most powerful magnetar flare ever observed occurred on December 27, 2004, from a magnetar designated SGR 1806-20, located tens of thousands of light years from Earth. Its initial spike lasted only a fraction of a second and had an inferred isotropic equivalent energy of order 10 to the 46 ergs, although the exact value depends strongly on the uncertain distance. That is comparable to the energy the sun radiates over roughly 100,000 years. Even across the galaxy, the flare produced a measurable disturbance in Earth's ionosphere. Magnetars may be relevant to one of the most puzzling phenomena in high-energy astrophysics: fast radio bursts. FRBS are millisecond-duration radio pulses of extraordinarily high brightness temperature, detected from cosmological distances, most of them originating billions of light years away. A typical cosmological FRB may release in milliseconds as much radio energy as the sun produces across all wavelengths over days or longer. Its instantaneous radioluminosity can briefly rival that of an entire galaxy. The first FRB was discovered in 2007 in archival data from the Parkes Radio Telescope, and many hundreds of sources and thousands of bursts have since been recorded, with numerous sources found to repeat. In 2020, an FRB-like burst was detected from within the Milky Way from a known magnetar, SGR 1935+2154, providing the first evidence that at least some FRBs are produced by magnetars. Though whether all FRBs have this origin or whether additional mechanisms are responsible for the most energetic extragalactic FRBs is still being investigated. Magnetars follow a different path. Their rotation periods are usually measured in seconds rather than milliseconds, and they slow rapidly. If their present spin down were powered only by ordinary magnetic dipole breaking, the inferred fields would reach the magnetar range. Their persistent X-ray luminosity can exceed the rotational energy they lose each second, showing that rotation alone cannot power them. Magnetic energy is the reservoir. The origin of such fields is still debated. One possibility is a dynamo operating in a very rapidly rotating proto-neutron star during the first seconds after collapse. Convection and differential rotation could amplify a seed field to enormous strength. Another possibility is that the progenitor star already possessed an unusually strong magnetic flux that was concentrated during collapse. Binary interaction and stellar mergers may help create the required rotation and field geometry. The field inside the star may be stronger than the dipole component inferred from spin down. Hidden toroidal fields can thread the crust and core. As the star cools and the crust solidifies, magnetic stresses continue to evolve. The field drifts through the crust by processes including Hall evolution and ohmic dissipation. Currents rearrange, concentrate, and decay, converting magnetic energy into heat. A magnetar outburst can begin when stress fractures or plastically deforms the crust, or when the external magnetic field becomes unstable. The event injects energy into the magnetosphere. X-ray brightness rises, pulse profiles change, and short bursts may repeat over days, or months. Most bursts are far weaker than a giant flare, but they reveal a persistent cycle of stress and release. The phrase starquake suggests a brittle crack, like an earthquake fault. Under the pressure inside a neutron-star crust, matter may instead deform through a mixture of fracture and plastic flow. The coupling between crust and magnetic field is complex. A small movement of the footpoints of field lines can twist the external magnetosphere. Currents flow along the twisted field and produce hard X-rays. Giant flares are rare. Only a handful have been observed from our galaxy and its satellites. Their initial spikes can briefly dominate the gamma-ray sky. A longer tail follows, modulated at the magnetar's rotation period as trapped hot plasma and radiation rotate in and out of view. The tail provides a direct measure of the spin even when ordinary radio pulses are absent. During some giant flares, quasi-periodic oscillations appear in the X-ray tail. These frequencies may represent vibrations of the crust, global magneto-elastic modes involving the core, or a coupled system of both. If correctly interpreted, they could become a form of neutron-star seismology. Different oscillation modes depend on crust thickness, magnetic field, and the properties of superfluid matter. The interpretation is difficult because the magnetic field couples regions that would otherwise oscillate independently. A frequency cannot always be assigned to a simple crustal mode. Future flares observed with instruments offering better timing and spectral resolution may separate the possibilities. Magnetars also challenge a simple division between neutron-star classes. Some high magnetic field radio pulsars have produced magnetar-like bursts. Some magnetars emit transient radio pulses after X-ray outbursts. A few objects have relatively modest dipole fields inferred from spin down, yet display magnetar activity, implying that strong internal or small-scale fields can remain hidden from the simple dipole estimate. This suggests that magnetar behavior may be a phase or capability rather than a completely separate kind of object. A neutron star's activity depends on age, internal field, crustal stress, external geometry, and thermal history. Some may be born as obvious magnetars and fade. Others may reveal magnetar-like behavior only after years of quiet. The connection to fast radio bursts is one of the most active parts of the field. In April 2020, the galactic magnetar SG R1935 plus 2154 produced an intense radio burst accompanied by high-energy emission. Seen from another galaxy, it would have resembled a relatively faint F or B. The event demonstrated that magnetars can produce at least some fast radio bursts. It did not prove that every F or B has the same mechanism. The most energetic extragalactic bursts can be far more powerful. Some sources repeat frequently. Some show complicated sub-bursts that drift in frequency. Polarization and rotation measures vary. Host galaxies include regions of active star formation as well as older stellar environments. Several magnetar-based models remain possible. A sudden rearrangement of the magnetosphere could launch a coherent radio pulse. A flare could drive a relativistic shock into surrounding plasma, producing a synchrotron maser. Different mechanisms may operate in different sources or even in different bursts from the same source. Repeaters allow astronomers to identify host galaxies and local environments. Some lie near persistent radio sources. One source resides in a globular cluster in a nearby galaxy, an environment not normally associated with very young massive stars. That discovery suggests that at least some F or B producing magnetars may form through channels such as compact object mergers or accretion-induced collapse rather than ordinary recent core collapse supernovae. Magnetars may also be engines for other transients. A rapidly spinning newborn magnetar could inject energy into an unusually luminous supernova. In some models, it can power a long gamma-ray burst or leave signatures in merger ejecta. Whether a remnant survives or collapses to a black hole changes the amount and duration of energy available. The magnetic field is invisible, but its consequences appear everywhere: in spin-down, X-ray heating, bursts, crustal motion, vacuum polarization, and radio flashes. A field generated in the first seconds of a neutron star's life can continue to shape events thousands or millions of years later. A magnetar does not need to rotate rapidly to be violent. It is a reservoir of stored stress. Its quiet appearance can last for years, while currents shift beneath the surface and magnetic configurations evolve. Then a small region changes, and a star only tens of kilometers wide becomes briefly detectable across the galaxy or beyond it. The collision of two neutron stars is one of the most energetic and scientifically productive events in the observable universe, and until 2017, it had never been directly observed. The detection of GW 170817 changed everything. On August 17, 2017, the LIGO and Virgo gravitational wave detectors recorded a signal lasting approximately 100 seconds, far longer than the brief fraction of a second signals from binary black hole mergers, and of a different character in its frequency evolution. The signal matched the expected pattern for two neutron stars spiraling together and merging, their orbital and spiral taking from a wide separation over millions of years down to the final merger in the seconds before the signal ended. The signal was strong in the two LIGO detectors. Virgo did not record a comparably strong signal because the source lay near a direction to which Virgo was relatively insensitive, and that absence helped the three observatory network localize the source to a region of about 28 square degrees. About 1.7 seconds after the gravitational wave signal, the Fermi Gamma Ray Space Telescope detected a short gamma ray burst from approximately the same direction. Short gamma ray bursts had long been hypothesized to originate from neutron-star mergers, but this was the first time a short gamma ray burst and a gravitational wave signal had been detected simultaneously from the same event, confirming the association. Within hours, dozens of observatories around the world had been alerted and were searching the localized sky region for an optical counterpart, the electromagnetic emission from the merger. The source was found in the galaxy NGC 4993, about 130 million light-years from Earth, as a new point of light first identified by ground-based telescopes and then followed by observatories on Earth and in space. The first optical counterpart to a gravitational wave event and the first confirmed kilonova, an optical and infrared transient produced by the synthesis and ejection of heavy radioactive elements in a neutron-star merger. The kilonova associated with GW 170817, designated AT 2017 GFO, was observed by dozens of telescopes at every wavelength from radio to X-rays over the following weeks. It brightened initially in the blue optical range, then faded while brightening in the red and infrared, a specific spectral evolution that matched the theoretical predictions for the production and decay of our process elements. The rapid neutron capture process, the R process, is responsible for roughly half of the solar system abundance of nuclei heavier than iron, including much of the gold, platinum, uranium, iodine, and many other heavy elements. It requires an extraordinarily neutron-rich environment, the kind of environment produced in a neutron-star merger. The R process had long been hypothesized to occur in neutron-star mergers and in certain types of supernovae, but the relative contribution of each site was uncertain. The kilonova spectrum obtained from AT 2017 GFO showed absorption features attributed to heavy R process elements, including a secure identification of strontium, while the presence and abundance of many heavier species had to be inferred from the overall color, opacity, and spectral evolution. The total mass of our process elements synthesized in the merger, inferred from the luminosity and spectral evolution, was estimated at roughly a few hundredths of a solar mass, a significant amount of heavy element synthesis in a single event. This detection established neutron-star mergers as a major site of our process nucleosynthesis and addressed one of the long-standing questions in nuclear astrophysics. Where do the heaviest elements come from? Gold, in particular, has been a focus of popular discussion. The gold in any ring, coin, or electronic component, the gold found anywhere on Earth, was produced in some combination of neutron-star mergers and possibly supernovae in the Milky Way's past, distributed through the interstellar medium by these events, eventually incorporated into the molecular cloud that formed the solar system, and then concentrated in rocky planetesimals and planets as the solar system assembled. Every piece of gold on Earth is a relic of a cosmic catastrophe that predates the solar system. GW 170-817 provided simultaneous electromagnetic and gravitational wave observations of the same event, a landmark achievement in what astronomers call multi-messenger astronomy. It confirmed that at least some short gamma-ray bursts are produced by neutron-star mergers. It provided the first direct evidence for kilonova and our process synthesis. It allowed a new, independent measurement of the Hubble constant from the gravitational wave signal's luminosity distance combined with the optical redshift of the host galaxy, contributing to the ongoing Hubble tension debate. And it constrained the neutron-star equation of state by setting limits on how large the neutron stars were. Large stars produce larger tidal deformations as they spiral together, leaving a detectable signature in the gravitational wave signal that constrains the equation of state. The tidal deformability measurement from GW 170-817 principally ruled out some very stiff equations of state that predict large radii and large tidal deformations. The existence of massive pulsars independently excludes many equations of state that are too soft to support stars above about 2 solar masses. Combined with X-ray pulse profile modeling, these observations support typical neutron-star radii of roughly 11 to 13 kilometers, while leaving important uncertainty about the deepest core. The final approach of 2 neutron stars unfolds across many timescales. For most of their lives as a binary, the loss of orbital energy is tiny. The stars circle in darkness for millions or billions of years. Their orbit shrinks almost imperceptibly. Only near the end does the process accelerate enough to enter the frequency band of ground-based gravitational wave detectors. Minutes before merger, the stars may still be hundreds of kilometers apart. They orbit faster and faster. The gravitational wave frequency rises, creating the characteristic chirp. Because neutron star systems remain in the detector band longer than heavy black hole binaries, the inspiral can contribute thousands of observable cycles. Those cycles allow precise measurement of a combination of masses called the chirp mass. During the earlier part of the signal, each star behaves almost like a point mass. Near the end, tides matter. The companion's gravity raises a deformation. The deformation changes the orbital energy and shifts the phase of the gravitational waveform. The effect is small, but it accumulates and carries information about the radius and internal pressure. The surfaces may come into contact while the orbital speed is a substantial fraction of light speed. Matter is squeezed, shocked, and torn into tidal tails. The outcome depends on the total mass, mass ratio, spins, and equation of state. A black hole may form almost immediately. A hypermassive neutron star may survive for milliseconds while differential rotation supports it. A longer-lived supermassive remnant may persist until magnetic braking and gravitational radiation remove support. A sufficiently low-mass remnant could remain stable. The lifetime of the remnant affects almost every messenger. prompt black hole formation can reduce some forms of ejecta. A surviving neutron star can drive neutrino-heated winds and inject magnetic energy. The accretion disk around the remnant launches outflows with compositions different from the matter pulled out tidally. The neutron richness of the ejecta determines which nuclei form. In the process, seed nuclei capture neutrons faster than radioactive beta decay can move them toward stability. The reaction path runs through extremely neutron-rich isotopes that cannot survive naturally on Earth. As the free neutrons are exhausted, the nuclei decay back toward stable forms, releasing energy that powers the kilonova. Different ejecta components produce different colors. Material with a relatively high electron fraction tends to form lighter or process elements and fewer lanthanides. Its opacity is lower, so radiation escapes earlier and appears bluer. More neutron-rich material forms lanthanides and possibly actinides. The enormous number of atomic transitions in lanthanides traps light, shifting the emission toward red and infrared wavelengths and stretching it over a longer time. This is why the color evolution of AT2017 GFO mattered. It was not simply a fading point of light. Its movement from blue to red encoded changing opacity and composition. The observed brightness implied that a substantial amount of matter had been ejected at high velocity. The spectrum securely identified strontium, while broader modeling supported the production of a wide range of processed nuclei. The gold comparison is powerful, but the cosmic inventory remains an active question. Neutron-star mergers unquestionably produce heavy elements. Ancient metal-poor stars show that our process enrichment occurred early in galactic history, sometimes in environments where the timing and mixing of rare mergers must be carefully considered. Some core collapse explosions involving rapid rotation and strong magnetic fields may also contribute. Collapsars, associated with the formation of black holes and long gamma-ray bursts, have been proposed as another major site. The relative importance of these sources may vary by element and by cosmic time. A neutron-star merger can produce a large mass of our process material in one event, but such mergers are rare and may occur long after the stars form. Rare classes of supernovae may act earlier. Chemical evolution models combine event rates, delay times, ejecta yields, and the mixing of material through galaxies. The atoms on Earth have passed through that long history. Heavy elements expelled from an ancient event mixed into interstellar gas. The cloud that formed the Sun inherited material from many earlier generations of stars. During planet formation, most gold followed iron into Earth's interior. The accessible gold in the crust was later concentrated by geological processes and may also have been supplemented by impacts after the planet's differentiation. A gold ring, therefore, does not point to one identifiable merger. Its atoms may come from several events, mixed beyond recovery. What can be said is that ordinary stellar fusion could not make them in abundance. Their nuclei required environments with enormous neutron fluxes and rapid, unstable nuclear reactions. GW170817 also tested the speed of gravity. The gamma-ray burst arrived about 1.7 seconds after the gravitational wave signal, following a journey of roughly 130 million light-years. The small delay showed that gravitational waves and light propagate at nearly the same speed, strongly constraining theories in which cosmic acceleration was explained by modifying gravity in ways that changed gravitational wave propagation. The event provided a standard siren measurement of cosmic expansion. The amplitude and evolution of the gravitational wave gave an absolute distance, while the host galaxy supplied a redshift. Unlike the traditional distance ladder, the method does not rely on calibrating one astronomical object against another. The first measurement was not precise enough to resolve the disagreement over the Hubble constant, but a population of mergers with identified hosts could become increasingly important. Short gamma-ray bursts require a relativistic jet aimed at least partly toward the observer. In GW 170817, the gamma-ray burst was unusually weak because the system was viewed away from the jet's central axis. Radio and X-ray emission brightened over months as the jet interacted with surrounding gas, and its beamed radiation spread into our line of sight. This afterglow allowed astronomers to infer a narrow, relativistic jet viewed off-axis. The event was therefore a sequence rather than a moment. Gravitational waves described the inspiral. Gamma rays marked the launch of high-energy outflow. Optical and infrared light traced radioactive ejecta. X-rays and radio waves followed the jet and shock. Each messenger sampled a different region and time. Future detectors will observe more mergers and may record the high-frequency signal after contact. The post-merger waveform would contain oscillation frequencies of the remnant and could constrain the equation of state more directly. Present ground-based detectors are least sensitive in that high-frequency region, but upgraded and next-generation observatories are designed to improve it. A nearby merger could also produce detectable neutrinos, though the expected event rate at such distances is low. If a long-lived remnant formed, its spin-down might create additional electromagnetic emission or a later gravitational wave signal. The diversity of outcomes will help reveal the maximum neutron-star mass and the role of phase transitions. Before 2017, much of this picture rested on separate lines of evidence. Binary pulsars showed that neutron-star systems lose energy to gravitational waves. Short gamma-ray bursts suggested compact mergers. Nuclear theory predicted our process ejecta. Kilonova models predicted a red-infrared transient. GW 170817 connected them within one source. It did not finish the story. It provided one well-observed event. The next nearby binary neutron-star merger may differ in mass, viewing angle, host galaxy, ejecta composition, and remnant lifetime. The value of the first event lies partly in how many questions it made possible to ask with real data. X-ray binaries are systems in which a neutron star accretes material from a companion star, producing X-ray emission that has been studied in detail by X-ray telescopes since the 1970s. When a normal star in a binary system with a neutron star expands as it ages or transfers mass through an intermediate stage, material can flow from the normal star onto the neutron star. This material, carrying angular momentum from the orbit, spirals inward through an accretion disk, heating through friction to temperatures of tens of millions of Kelvin and emitting X-rays. The neutron star's strong gravity, surface gravity about 100 billion times Earth's, means that the infalling material releases a large fraction of its rest mass energy as radiation, making X-ray binaries among the most luminous objects per unit mass in the galaxy. X-ray pulsars, neutron stars and binaries with strong magnetic fields that channel the accreting material onto the magnetic poles, pulse in X-rays as the magnetic poles rotate in and out of view. X-ray bursters, accreting neutron stars whose surfaces accumulate material until thermonuclear runaway ignites the accreted layer, produce brief bursts of X-ray emission after enough fuel has accumulated, with recurrence times that can range from hours to days depending on the system and the accretion rate. These Type 1 X-ray bursts are thermonuclear explosions on the neutron star surface, brief events of extraordinary brightness that can be observed in detail by X-ray telescopes. The detailed observation of X-ray burst profiles, particularly the oscillations during bursts that reflect the rotation of the neutron star as the burning region spreads across the surface, has provided information about neutron star rotation rates and surface gravity, contributing to constraints on the equation of state from a completely different direction from gravitational wave observations. Some X-ray binary neutron stars accrete at very high rates, close to or exceeding the theoretical Eddington luminosity limit, and can produce relativistic jets of material flowing outward at near light speed, visible as radio sources on parsec scales, and qualifying the system as a microquasar, a small-scale analog of the quasars seen in distant galaxies. The jet physics of microquasars, studied in detail because of their proximity compared to actual quasars, contributes to understanding of jet formation and propagation in the more powerful jets of active galactic nuclei. Accreting neutron stars reveal the surface in ways isolated pulsars cannot. Matter arriving through a disk loses orbital energy through friction, magnetic stresses, and radiation. Close to the star, the disk may meet the surface directly or be interrupted by the magnetic field. If the field is strong, plasma follows field lines toward the magnetic poles and forms accretion columns. As gas decelerates, it creates X-rays. The rotating columns produce regular pulses, but unlike a radio pulsar, the power source is the gravitational energy of accretion. Changes in the mass transfer rate alter the brightness and the torque. The neutron star may spin up when the disk transfers angular momentum efficiently and spin down when magnetic coupling or outflows dominate. Cyclotron resonance features in X-ray spectra provide some of the most direct magnetic field measurements in astronomy. Electrons moving around magnetic field lines occupy quantized energy levels. Photons at the corresponding energy are absorbed or scattered, producing a feature whose position depends on field strength and gravitational redshift. In some systems, these lines imply fields of around 1 trillion Gauss. In lower field systems, material spreads across more of the surface. Hydrogen and helium accumulate in a thin layer. The underlying gravity compresses and heats the fuel. Because the gas is degenerate or nearly degenerate, rising temperature does not immediately cause the layer to expand and cool. Nuclear burning can become unstable. A Type 1 X-ray burst begins when the fuel ignites. Within seconds, the X-ray luminosity can increase dramatically. The burning front spreads around the star. The burst then fades over tens of seconds or minutes as the layer cools. Repeated bursts allow the same neutron star to be observed under different fuel and accretion conditions. Some bursts become bright enough for radiation pressure to lift the photosphere above the surface. These photospheric radius expansion bursts approach the Eddington limit, where outward radiation force balances gravity for the atmospheric material. They have been used as distance indicators and to constrain mass and radius, though uncertainties in composition, atmosphere models, and geometry complicate the inference. Rare superbursts last for hours and are thought to ignite carbon deeper in the accumulated ocean. Their long recurrence times and enormous energy probe heat flow, crustal reactions, and the composition of ashes left by ordinary bursts. Between bursts, stable nuclear burning and electron captures transform the accreted material as it is buried. The crust of an accreting neutron star is not identical to the crust of an isolated one. Fresh matter pushes older material downward. Nuclei undergo sequences of electron captures, neutron emission, and fusion reactions. These reactions deposit heat in the crust. When an X-ray transient returns to quiescence after years of accretion, astronomers can watch the heated crust cool back toward equilibrium with the core. Such crust cooling curves measure thermal conductivity and heat capacity. A highly conductive crust relaxes quickly. Impurities and disordered pasta can slow heat flow. Additional shallow heating appears to be required in some sources, indicating that not all energy release processes in accreted crusts are understood. Accretion can also produce kilohertz quasi-periodic oscillations in X-ray brightness. Their exact origin remains debated, but their frequencies are comparable to orbital motion close to the neutron star. They may reflect structures in the inner disk, boundary layers, or oscillations. Because the frequencies approach 1,000 cycles per second, they probe motion only tens of kilometers from the surface. Some accreting neutron stars show coherent millisecond X-ray pulsations, directly revealing fast spin. Others reveal spin through burst oscillations, slight brightness modulations during thermonuclear flashes. The distribution of spins cuts off well below the most extreme theoretical breakup frequencies. Magnetic torques, gravitational wave emission, or limitations in accretion may prevent further spin-up. Accretion disks can launch winds and jets. Neutron star jets are generally less powerful than the most extreme black hole jets, but they show that an event horizon is not required for relativistic outflow. Comparing neutron star and black hole binaries helps isolate the roles of a surface, magnetic field, and inner disk boundary. In a black hole binary, matter can disappear through the horizon. In a neutron star binary, accreting gas must ultimately interact with a surface or magnetosphere. That difference changes the spectrum and energy budget. Boundary layer emission can reveal the final deceleration of gas from orbital speed to the rotation speed of the star. X-ray binaries are also evolutionary bridges. Continued accretion can weaken or bury the magnetic field and spin the star toward millisecond periods. When the donor star contracts and mass transfer stops, the disk fades. The rotation-powered pulsar can reappear. The quiet millisecond pulsar is therefore the afterlife of an X-ray binary. The equation of state of dense nuclear matter is the central unknown in neutron star physics, and the multi-pronged observational campaign to measure it is one of the most active areas of current astrophysics. The equation of state determines the relationship between pressure and density in neutron star matter, how much pressure is generated at a given density. A stiff equation of state means matter is relatively incompressible, producing larger radii at a given mass and generally allowing a higher maximum mass. A soft equation of state means matter is more compressible, producing smaller radii and generally a lower maximum supported mass. The cold, neutron-rich matter of a neutron star core cannot be recreated directly in a laboratory. Heavy ion collisions can briefly reach enormous densities and temperatures, but the matter they produce is hot, short-lived, and compositionally different from the long-lived matter inside a neutron star. Constraints come from several observational probes. The maximum mass constraint requires the equation of state to be stiff enough to support at least 2 solar masses, since neutron stars of this mass are known to exist. Masses are measured most precisely for pulsars and binary systems through the orbital dynamics and the Shapiro delay, a general relativistic effect in which the pulsar signals are slightly delayed when they pass close to the companion star in its orbit, an effect measurable with high-precision pulsar timing and dependent on the masses of both stars. The radius constraint comes from X-ray observations of neutron star surfaces. The NICER telescope, Neutron Star Interior Composition Explorer, is a NASA instrument on the International Space Station specifically designed to constrain neutron star masses and radii by modeling the X-ray pulse profiles from hot spots on rotating neutron star surfaces. NICER's precise pulse timing, combined with detailed modeling of how the hot spot emission is Doppler shifted and gravitationally beamed as the star rotates, allows the simultaneous inference of the neutron star mass and radius to a precision that constrains the equation of state. The tidal deformability constraint from gravitational wave observations, as described in the context of GW 170817, constrains the equation of state through how easily the neutron stars are deformed by each other's tidal gravity in the final orbits before merger. The nuclear physics constraint comes from terrestrial experiments that measure the properties of nuclear matter at slightly subnuclear density, the density of atomic nuclei, and attempt to extrapolate to higher densities using nuclear theory. The chiral effective field theory approach, which systematically builds nuclear interactions from the underlying quark-gluon physics of quantum chromodynamics at low energies, provides the most theoretically controlled framework for this extrapolation, but it is reliable only up to about twice nuclear saturation density. Above that, uncertainty grows. The combination of all these constraints, maximum mass, radius, tidal deformability, and nuclear theory, has significantly narrowed the allowed equation of state in recent years. The picture emerging is of neutron stars with radii roughly in the range of 11 to 13 kilometers for a typical neutron star, a result inconsistent with some of the most extreme soft equations of state. Current data do not yet determine whether hyperons, condensates, or deconfined quark matter appear in the cores of the most massive neutron stars. Resolving that question is one of the central goals of future gravitational wave observations, X-ray measurements, and nuclear theory. The evolution of a neutron star over time follows a trajectory from the enormous temperatures of its birth to the cold, dark remnant it will eventually become. At birth, immediately following the supernova, a neutron star is extraordinarily hot. The proto-neutron star reaches temperatures of 100 billion Kelvin or more, and at these temperatures it is not yet fully a neutron star in the sense described above. It is a dense, hot fluid of neutrons, protons, and leptons, opaque even to neutrinos, which are produced in enormous numbers by the rapid-fire neutronization occurring throughout the collapsing core. The subsequent neutrino emission carries away roughly 99% of the gravitational binding energy released in the collapse within a few tens of seconds. Only a small fraction appears as the kinetic energy and electromagnetic light of the supernova, even though that visible explosion can briefly outshine an entire galaxy. During the first seconds and minutes, the newborn neutron star cools dramatically as neutrinos escape and the interior settles. Over the next thousands of years, it continues to cool, with thermal X-rays becoming the most direct electromagnetic trace of its hot surface. This cooling is a complex process involving several mechanisms: neutrino emission from the still hot interior, the modified Urca process and related reactions, conduction of heat through the neutron star's crust, and the gradual development of the superfluid and superconducting phases in the core that alter the thermal properties. The cooling rate constrains the equation of state and the internal structure because different phases of matter cool at different rates. The reported rapid cooling of the neutron star in Cassiopeia A, a very young object in a roughly 350-year-old supernova remnant, has been interpreted as evidence that neutron superfluidity began developing in part of the core, temporarily increasing neutrino emission through pair formation and breaking. The exact cooling rate and interpretation remain debated, illustrating both the power and the difficulty of using surface temperature to probe the interior. Over millions of years, a neutron star that is not accreting, an isolated neutron star, cools slowly until its surface temperature falls to a few 100,000 Kelvin, at which point it is primarily emitting X-rays in the soft X-ray range. Over billions of years, it cools further, eventually becoming a cold, dark neutron star emitting very little electromagnetic radiation and drifting through the galaxy almost invisibly. The very oldest neutron stars in the galaxy may already be approaching this state. Neutron stars in globular clusters, some of which are 12 billion years old, have been spinning for far longer than the solar system has existed. Those that have accreted from binary companions may have been recycled into millisecond pulsars. Those that have not accreted have been cooling for 10 billion years and are likely very cold and very faint. Cooling exposes another hidden competition. A young neutron star loses energy mainly through neutrinos from its interior. Later, photons from the surface become more important. The transition depends on age, mass, composition, superfluidity, magnetic field, and the insulating properties of the envelope. The envelope is only a shallow outer layer, but it controls the relation between internal temperature and surface temperature. Light elements conduct heat differently from heavy elements. Two stars with similar interiors can therefore show different surface temperatures if one has a hydrogen-rich envelope and the other an iron-rich one. Strong magnetic fields make heat transport directional. Energy moves more easily along field lines than across them. A magnetary star can develop hot polar regions and cooler zones elsewhere. A single measured temperature may hide this uneven pattern. Superfluidity changes both heat capacity and neutrino emission. When neutrons or protons pair, many ordinary reactions are suppressed because energy is required to break the pairs. But the formation and breaking of pairs also creates a temporary neutrino emission channel. A cooling curve can therefore change slope when a region crosses its critical temperature for superfluidity. The interpretation of the Cassiopeia, a neutron star, illustrates both the promise and difficulty. Observations suggested a noticeable temperature decline over a decade. One explanation invoked the onset of neutron superfluidity in the core. Later analyses found that calibration and modeling choices affected the inferred rate. The source remains valuable, but it also demonstrates how demanding precision cooling measurements can be. Older neutron stars may be reheated. Friction associated with superfluid vortices can convert rotational energy into heat. Magnetic field decay heats magnetars. Accretion from the interstellar medium is usually weak, but in some environments it may contribute. Dark matter heating has also been proposed as a possible effect, though no such signal has been established. The internal quantum states of a neutron star, the superfluidity and superconductivity of its interior, produce observable effects that are otherwise impossible to study. Neutron star superfluidity was first theoretically proposed by Arkady Migdal in 1959, shortly after the theory of superconductivity was developed by Bardeen, Cooper, and Schrieffer. A superfluid of neutrons would have no viscosity. It would flow without friction and circulate indefinitely without slowing. A rotating superfluid is quantized. Instead of rotating smoothly, it circulates around an array of quantized vortices, each carrying one unit of angular momentum. As the neutron star spins down, losing angular momentum due to electromagnetic radiation, the vortices migrate outward. The observable consequence of neutron star superfluidity is the pulsar glitch. Most pulsars spin down smoothly over time, losing angular momentum to electromagnetic radiation at a steady rate. But some pulsars, particularly young ones, occasionally spin up suddenly. The rotation rate jumps abruptly by a tiny amount, then resumes its slow spin down. These sudden increases in rotation rate are called glitches, and they are thought to reflect the sudden transfer of angular momentum from the interior superfluid, which may have been rotating slightly faster than the crust, to the crust and observable rotation rate of the pulsar. The glitch mechanism involves the unpinning of superfluid vortices from the crustal lattice, allowing a sudden transfer of angular momentum that spins up the observable crust. The size and frequency of glitches constrain the fraction of the neutron star's moment of inertia that is in the superfluid component, and therefore the size of the superfluid region. The Vela pulsar, one of the most prolific glitchers, experiencing large glitches roughly once every 3 years, has been used to constrain the moment of inertia of the superfluid component. The analysis suggests that a significant fraction of the star's interior is in a superfluid state, consistent with theoretical predictions for the neutron star interior, but providing compelling astronomical evidence that a substantial superfluid component exists inside the star. Glitches provide a different window into the same interior. The crust and charged components are coupled to the external electromagnetic torque and gradually slow. A superfluid component can retain a slightly higher rotation rate. Quantized vortices carry its angular momentum. If vortices pin to structures in the crust, the lag grows. When many vortices unpin or move outward, angular momentum is transferred to the crust. The observed rotation frequency jumps. The largest Vela glitches change the spin by only a few parts in a million, but pulsar timing measures them easily. The increase can occur in seconds or less. After a glitch, the pulsar often relaxes. Part of the frequency change decays over days, months, or years. Different relaxation times may represent different superfluid regions recoupling to the crust. Some changes remain permanent. The spin-down rate can also shift. Not every glitch follows the same pattern. The crab pulsar glitches relatively often, but usually by smaller amounts than Vela. Some magnetars glitch near radiative outbursts. Rare anti-glitch events have been reported in which the observed star suddenly spins down. These may reflect changes in the interior, magnetosphere, or both. The amount of angular momentum available in the crustal superfluid became a puzzle when more realistic calculations included entrainment. Neutrons moving through the crustal lattice are not entirely free. Interactions increase their effective inertia and reduce the independently flowing reservoir. Some analyses suggested that the crust alone could not explain large glitches. A contribution from coarse superfluid, different entrainment strength, or revised stellar structure may be required. This is a powerful example of how one tiny timing irregularity reaches deep into nuclear physics. A pulse arrives early by a fraction of a rotation. From that, astronomers estimate the moment of inertia of an invisible quantum fluid beneath a crust thousands of light years away. Neutron-star oscillations offer further possibilities. The star can support pressure modes, gravity modes, crustal shear modes, and spacetime modes. A merger can excite them. A magnetar flare may reveal them. An unstable rotating mode called an R mode could emit gravitational waves and limit spin, although direct evidence remains absent. Continuous gravitational waves might also come from a slight permanent deformation, sometimes called a mountain. The mountain need not resemble a geological peak. It may be a tiny asymmetry in density produced by crustal strain, magnetic fields, or accretion. As the star rotates, the changing quadrupole moment emits gravitational radiation at a nearly constant frequency. Searches have placed increasingly strict upper limits on such emission from known pulsars. For some objects, the limits are below the level that would account for all observed spin down. This means most of their rotational energy must be lost electromagnetically rather than through gravitational waves. A future detection would measure asymmetry far smaller than any telescope could image. Cooling, glitches, oscillations, and continuous waves all observe the star indirectly. None provides a cross-section. Together, they reveal heat capacity, superfluid coupling, elasticity, magnetic stress, and internal symmetry. The neutron star behaves like a sealed instrument whose interior can be inferred only from the way it rings, cools, and turns. Proton superconductivity in the neutron star core produces an additional exotic effect. If the proton component forms a Type II superconductor, much of the magnetic flux is organized into quantized flux tubes, analogous to the quantized vortices in the neutron superfluid. The slow interaction of these flux tubes with neutron vortices and the crust may contribute to the long-term evolution of pulsar magnetic fields, although the details remain uncertain. The Milky Way should contain far more neutron stars than the catalogs show. Core collapse supernovae have occurred throughout the galaxy's history. Even a modest long-term rate produces hundreds of millions of remnants. Most are old, cold, and no longer beam toward Earth. Some may pass within a few tens of light years without being noticed. A quiet neutron star does not sweep up matter like a cosmic vacuum cleaner. Its physical size is tiny, and interstellar gas is sparse. Unless the star moves slowly through a dense cloud, accretion remains faint. High birth velocities make detection even harder. Several observational families fill parts of the gap. The Magnificent Seven are nearby, thermally emitting isolated neutron stars discovered in soft X-rays. They have no obvious binary companions and relatively long rotation periods. Their spectra and magnetic features allow detailed study of cooling surfaces. Central compact objects sit near the centers of young supernova remnants. They emit thermal X-rays, but often lack the strong radio pulsations and bright wind nebulae expected from ordinary young pulsars. Some have surprisingly weak inferred dipole fields and are sometimes called anti-magnetars. Their fields may be buried by fallback material and later re-emerge. Neutron stars can also reveal themselves through gravitational microlensing. As a compact object passes close to the line of sight to a background star, its gravity bends and magnifies the light. Measuring both photometric brightening and astrometric deflection can estimate the lens mass. This method may eventually identify isolated neutron stars that emit almost nothing. Future radio observatories, especially the Square Kilometre Array and its pathfinders, are expected to discover many more pulsars. Greater sensitivity will reach distant and faint sources. Better computing will search tight binaries and extreme accelerations. The galactic center, globular clusters, and nearby galaxies remain important targets. Future gravitational wave observatories will extend neutron star astronomy in another direction. More sensitive ground-based detectors will record mergers farther away and with greater detail. Third-generation instruments may observe binary neutron stars for hours, provide earlier warnings to telescopes, and detect post-merger signals. Space-based detectors could observe some compact binaries at lower frequencies before they enter the ground-based band. Though ordinary neutron star binaries are challenging targets until relatively late. X-ray timing and spectroscopy will continue to refine masses, radii, hotspot geometry, magnetic fields, and cooling. A single new high-mass neutron star with a precise radius could remove many equations of state. A well-measured moment of inertia in the double pulsar would add an independent constraint. A nearby giant magnetar flare could expose oscillation modes with unprecedented clarity. The most decisive discovery may be something not yet represented in the existing categories. The first pulsar was found in an experiment built for another purpose. The first fast radio burst was recognized in archived data. The first binary neutron star merger connected signals that had previously been studied separately. Extreme objects often become legible only after instruments learn to observe them in a new way. A neutron star is sometimes described as the corpse of a star. The phrase captures the end of fusion, but it misses the continuing activity. A neutron star can radiate, spin, glitch, accrete, burst, launch jets, power a nebula, distort spacetime, merge, and manufacture heavy nuclei. It is not a passive cinder. It is a new physical object created by the death of the old one. The original star may have been millions of kilometers across. Its remnant is the size of a city. The reduction in scale is so extreme that it brings the quantum structure of matter into direct competition with gravity. Every observable property follows from that compression. Mass determines curvature. Radius determines compactness. Composition determines cooling. Rotation creates a clock. Magnetic field creates a magnetosphere. A companion turns the clock into a gravitational laboratory. A merger converts the laboratory into an explosion that can seed galaxies with new elements. The deepest questions remain open. We do not know the exact maximum mass. We do not know whether deconfined quarks occupy the core. We do not fully understand coherent radio emission. We do not know why some neutron stars become magnetars or which mechanisms produce every fast radio burst. We do not yet know the full cosmic balance between mergers and other process sources. These uncertainties do not make neutron stars less understood than other objects. They make them especially useful. Each uncertainty corresponds to a measurable signal, a radius, a pulse shape, a cooling rate, a merger phase, an oscillation frequency, or a timing residual. The star remains inaccessible, but not silent. It sends information through radio pulses, X-rays, gamma rays, neutrinos, and gravitational waves. It records the physics of its surface and spectra, the physics of its interior in glitches, and the physics of spacetime in orbital timing. A dense object drifting in darkness may appear almost absent from the universe. Yet its existence is a stored history of stellar burning, collapse, nuclear transformation, and gravity. Even when it no longer pulses, it remains one of the most extraordinary arrangements of matter nature can sustain. Neutron stars have also changed the broader relationship between astrophysics and fundamental physics. Neutron stars bring general relativity, quantum mechanics, electromagnetism, and both the strong and weak nuclear interactions into the same object. Gravity determines the global structure. The strong force helps determine the pressure of dense matter. The weak interaction controls neutronization and much of the cooling. Electromagnetism shapes the crust, atmosphere, and magnetosphere. Quantum mechanics is present throughout, making them natural laboratories for the physics that operates when all these frameworks must simultaneously apply. The precision of pulsar timing has made pulsars into precision tools for fundamental physics in ways that were entirely unanticipated when the first pulsar was discovered. The measurement of the Shapiro delay in pulsar binary systems tests general relativity in the strong field regime with a precision exceeding many laboratory tests. The orbital decay of the Hulse-Taylor binary confirmed the existence of gravitational waves before LIGO detected them directly. The pulsar timing array evidence for a nanohertz gravitational wave background opened a new observational window on the universe. The tidal deformability measurement from GW170817 constrains the strong force equation of state in ways unreachable in terrestrial experiments. This multi-directional scientific productivity from a single class of objects, using them simultaneously as laboratories for nuclear physics, general relativity, and gravitational wave astronomy, illustrates how the extreme conditions in neutron stars make them uniquely valuable objects of study. The discovery that neutron star mergers produce large amounts of our processed material, including gold and platinum, is perhaps the neutron star finding most directly connected to ordinary human experience. Gold has been a currency and an object of value for 10,000 years of human civilization. Understanding where it comes from, understanding that much of it was synthesized in the neutron-rich aftermath of compact cosmic explosions, including neutron star mergers, ejected into space in a kilonova explosion, dispersed through the interstellar medium, incorporated into the solar nebula, and concentrated by geological processes into the veins and deposits we mine today, is understanding a chain of causation that stretches from the first stars to the present, from the most violent events in the universe to the most mundane. The neutron star in the Crab Nebula is the most directly connected neutron star to human history. The supernova that produced it was recorded in 1054 by Chinese astronomers and in surviving Japanese records. Proposed references in other traditions, including possible rock art in the American Southwest, remain debated and should be treated cautiously. European chronicles are largely silent on it, and the reasons for the silence have been debated by historians. Perhaps the event coincided with political upheaval. Perhaps the bright star was simply not recorded in the surviving documents. Perhaps records were lost. What we know is that on July 4th, 1054, a brilliant guest star was recorded in the constellation Taurus that was visible in daylight for about 3 weeks and in the night sky for roughly 2 years. The object known today as the Crab Nebula, the expanding shell of gas and the pulsar at its center, is what remains of that explosion. The pulsar spins 33 times per second. It powers the nebula around it, driving the synchrotron emission that makes the Crab one of the brightest radio and X-ray sources in the sky. It loses rotational energy at a rate of about 5 times 10 to the 38 ergs per second, or about 5 times 10 to the 31 watts, roughly 130,000 times the luminosity of the Sun, all from the pulsar spin down. The Crab pulsar has been observed to glitch multiple times, providing some of the clearest data on pulsar glitch mechanics. It has long been used as a calibration source for X-ray and gamma-ray telescopes because of its brightness, although modern observations have shown that parts of the nebular emission can vary, and it connects a specific human historical observation, the record of a bright new star in Chinese chronicles in 1054, to a specific physical object, a rotating neutron star 20 kilometers across, spinning 33 times per second, 1,000 years later. That connection, across a millennium, across the distance of about 6,500 light-years, from a historical note in a medieval chronicle to a rapidly spinning remnant of stellar death, is one of the more vertiginous examples of how astrophysics and human history sometimes intersect. A neutron star spinning hundreds of times per second at the center of a nebula, producing precision pulses of radio emission so regular that they were initially mistaken for an artificial signal, is the endpoint of a star that once shone for millions of years, providing light and heat to whatever vicinity it occupied, building carbon and oxygen and heavier elements in its interior, and then dying in an explosion so brief and so violent that its entire history of burning was trivial by comparison. What remains, 20 kilometers across, containing more mass than the Sun, made of compressed nuclear matter in states that no laboratory can reproduce, spinning, cooling, pulsing, is in some ways the most physics-rich object in the universe per unit volume. Everything that happens inside one is beyond the reach of ordinary experience. And yet every pulse of radio emission that arrives at our telescopes from a millisecond pulsar is carrying, encoded in its exact arrival time, information about the orbital dynamics of its binary system, the gravitational field of its companion, the properties of the space between us, and the interior physics of the star itself. The universe, when it makes something extreme, makes something extraordinarily legible to those patient enough to listen to the signal. There are now more than 4,000 cataloged pulsars, most of them in the Milky Way. There may be hundreds of millions of neutron stars in the galaxy, most of them dark and old and undetectable, drifting through the interstellar medium after their pulsing years have ended. They have been there since before the solar system formed, since before Earth existed, since before any atom in your body was assembled into anything biological. The oldest of them are cold and dark, and the universe has largely forgotten them. But they are real. They are there. Dense, exotic, extraordinary in every cubic centimeter. The most extreme matter in the observable universe, and the most scientifically productive that extreme matter has ever been. Good night.